So it's my pleasure to do this introduction. I would also like to take the opportunity to thank Jeannette and Judith for organizing this first school from IS-ENES-3 project. So on the modeling of the Earth's climate system, I'm not fully sure of all your background for all of you. Just a reminder for most of you. The main objective of modeling the Earth's climate system or climate models is to help us understand mechanism, but also predict or project whatever climate variability and change. So be able to say something about possible changes. This overall picture summarizes the main components of climate models. You will have the atmosphere that is represented top left. The ocean is represented on the right. The surface, whether it's characteristic like vegetation cover, and also the transfer from ocean to through the atmosphere from ocean to land. And down below, the anthropogenic forcing, so that like the emissions of different gases. And all that is represented in the center within boxes in the atmosphere and ocean, discretized in the atmosphere and ocean. So those models have evolved through time. And it started mainly in the mid-70s, where at start it was mainly the atmosphere and surface and simplified land surface. Ocean and sea ice at the start was often just a surface layer, which is the first one interacting, a kind of buffer for energy. There was no circulation in the ocean. And then through time, the models have got more complex with full coupled atmosphere-ocean models for what is called FAR is the first assessment report. So this is a diagram from IPCC, and you have the references associated with IPCC. So FAR is the first assessment report that was in 91. The second one in 95. The third one was in 2001, AR4 2007, AR5 2013. And the community is now preparing the RR6, which is going to be published in 2021. And at each time, so we started with the atmosphere, more and more complex, which is synthesized by the size of the boxes, the land surface, the ocean. Those three are the main components, but then was added aerosols. First, they were prescribed and then computed. The carbon cycle, that was mainly at the beginning of the 2000s. The dynamic vegetation, in fact, which is not that much systematically included. So it's really more in AR5, there were only two couple models really with dynamic vegetation. Now we hope that there is a bit more. Atmospheric chemistry and land ice. So this diagram is a bit optimistic in the sense that, yes, you begin to have models including, for example, land ice, but it's not at all systematic. But it gives you a way of how we progress by adding progressively the different components. Another way to represent these models, which are also called Earth system models, what we call climate, in fact, they are all climate models. What I like to use is Earth climate system models because they only represent the climate system part of the Earth, not all the Earth system. They have the physical components, so the atmosphere, the ocean, the land surface, coupled through a coupler. And you have the biogeochemical cycles. It's when you add the biogeochemical cycles that they really become Earth system models. Otherwise, they are usually called GCMs, ocean atmosphere coupled GCMs, general circulation models, or in fact, GCM is more and more used to say global climate models. But originally it was global general circulation models. So saying that we are really describing in detail the atmospheric and the ocean general circulation. So those models are based on the basic physics of the system. So on Navier-Stokes for the dynamics, and various conservation laws like energy, mass, for air, for water, for carbon. So this is very important that they are really based on the physical principles. And they include what we call parametrizations, because not all the scales can be explicitly resolved with basic equations like clouds. Clouds, it occurs at a range of scales. And when we are at 100-kilometer scale, you can clearly see that we cannot really resolve exactly what happens at the microphysics. So we will parameterize those with simpler. It's not a direct equation from the physics, but it's based on physical principles. Like, for example, for clouds, if air becomes oversaturated, supersaturated, then you have precipitation of the excess of water vapor. Or if the atmospheric column is unstable, you will represent this instability to represent convective clouds, for example. So you will take into account the conservation of mass, typically conservation of energy, but you will represent in a schematic way what happens in clouds, radiation, surface fluxes also, which are turbulent fluxes that can also be explicitly represented. Those are very small scales. Or other subscalar processes like the representation of ADs in the atmosphere and ocean, or the turbulence in the first 2 kilometers of the atmosphere, which is the boundary layer, which is also quite turbulent, and that plays a key role of having the energy exchanges at the surface going to the troposphere layers of the atmosphere. I don't know if this notion of parametrization is clear for everybody, but if you do not see any specific question, but it's important that we have those two aspects. So basic laws and parametrization. Parametrization also accounting for basic laws. You have to realize that those Earth system models represent an enormous amount of work accumulated through time with a lot of people working on this. You have specialists of the atmosphere, of the land surface, of the ocean, of the sea ice, of the chemistry, vegetation, ocean. I think it's about 500 to 1,000 man-years. So that's typically, we are in the range of 1,000 man-years accumulated over the last 30 years. So there is a strong legacy of those models, and they are quite heavy tools and not just a tool of one person. On the spatial resolution, because those models taking the equations, they are discretized over grids. So the atmosphere and the ocean are divided into grid box. In each grid box, you will have a mean temperature, mean precipitation, a mean wind, mean pressure, and you will compute the exchanges with the neighbors. In the TAR, so that's in the 2007, 2007 time, they were the highest resolutions were in the range of 180 kilometer. In AR4, that is 2013, it was in the 110 kilometer, and now in the diagram on the right were the ones from the last IPCC reports, with some common range in the 100 kilometer again, and the highest in our AR6 is we reach about 30 kilometer. But most of the models are still in the 100, 150 kilometer configurations, with some configuration even higher. What you can see for those with those diagrams is that it has a strong impact on how you represent topography. So the topography and the land-sea contrast are two key elements for which the spatial resolution plays a key role. So the common range, we are really in this 100, 150. And if we take this diagram showing the different scales of interaction that was produced by Stammer et al. In 2018, and you can see that in the atmosphere, you have a range of scales as well as the ocean. The row above is the atmosphere, and the row below is the ocean. And typically with climate models, we are in this 120, 200 or down 25 at best. And you see that that means that we can represent some large scale ADs, but not, of course, in details, the clouds and the small scale ADs, and the same in the ocean. In the time, which is on the other axis, most models, the time step is of the orders of minutes. And we have to simulate hours, days, months, years, decades, or even millennia when we talk about past paleoclimates. So we have really a range of timescales, a range of spatial scale to represent. This is what we can do, and the choice of spatial scale which is resolved is highly dependent on the computing time available. And to really do climate simulations, you need to have something what we call simulated years per day. So per day of computing, how much years you can simulate. And typically you have to be in the above the 5 simulated years per day. In weather, you can manage with 100 simulated days per day, but for climate, you need much more than this because you have much longer integration time. The next, okay. This there is a strong work of evaluation of those models, and class will elaborate more on this. And here is a diagram which summarizes the status at different time of those models associated with IPCC. So it is a diagram from the last IPCC reports. And what is called SEMIP 3 and were the models in the 2005 period, and SEMIP 5 in 2012. And I will elaborate more on what is SEMIP and give you a bit more perspective, but let's take it as a time when we look at the ability or capability of the models. And this diagram is interesting to show you a number of things. It shows you the correlation with observations. That's the y-axis. And on the x, you have 4 variables: the surface air temperature, the long wave outgoing radiation, precipitation, and the short wave cloud radiative effect. Each model is a small bar, and you have the median of the models, which is the circle, and the longest bar is the ensemble mean of, so you have the mean and the median of the different models. For what you can see is, and the observations are in green, sorry. What you can see is that models perform much better for temperature than for precipitation. You can also see that the uncertainty between models is bigger for precipitation than for temperature. For radiation, you can also see that models perform much better for long wave outgoing radiation than for the short wave cloud radiative effect. And for the short wave cloud radiative effect, you can see that you have a wide range between the different models. And this is one of the main sources of uncertainty, and I will come back on this again. And yes, in green, no, let me be a bit more precise. You have one set of observations which is used as a reference. So the one is the level 1 is the reference for reference observation, and the green is another set of observations showing you that you have not much, you have very small uncertainty in the different set of observations for temperature, but you have more uncertainty when you look at precipitation. So there is also uncertainty in the observations themselves, not only in the models. Just to have one look at maps, you have the multi-model mean precipitation. That's an annual mean precipitation from SEMIP 5 again, so the last IPCC report. And below the multi-model mean bias, which shows you that there are biases in those models. So even when you take the multi-model mean, you have biases, particularly in the tropics, more than in the mid-latitudes. And on the right, you see the multi-model mean relative error. This is the error of the different models relative to the multi-model mean. And you see that you have a range which is quite high, especially in the tropics, between the models relative to the mean. In practice, in most cases, the multi-model mean of models is often better than just individual models. So we tend to recommend to use multi-model means rather than just one model, or at least to take a range of models and never just use one model results, because you have then too much uncertainty in just using one model. So you need to take into account the model uncertainty with that. Those models, they perform better at large regional scale than at small scale. Let's take two different examples. Above, it's to look at the extremes. So those and the extremes for different regions. And it's so each box is a different region on the right. And you have the models, the range of models that are in gray. I'm sorry, the diagram is not that easy to read, but you have the light gray boxes that are SEMIP 3, the dark gray boxes that are SEMIP 5, and you have a range of observations. It shows you that for most regions, models are more or less in the range of the observations. And this is for the maximum, the hottest days, temperature for the different regions in average, in climatological average for the period 1981 to 2100. And so you see that they are more or less in the range, so they perform not that bad for extreme. You also see that there are uncertainties in the different observations and between the different reanalyses, and that in fact the uncertainty of the models are often also in the uncertainty of the observations. That's for large regions. Let's look at the diagrams below that are quite interesting and that look at different scales and compare smoothing scales. So when you look at the models at a small scale, so directly at the grid scale, and then you consider them by smoothing at larger scales and compare them with observations. So that's the error compared to observations. And you can see that the error is very small when you are at large scale. So when you look at global averages, but then they increase much more when you are at more local scales, with often some outliers. You can see that for some temperature, you have some models that are completely out, but they are the others are more grouped. And you see that the error is also increases more at small scale for precipitation than for temperature. So it shows you that the models are better at large scale than at small scales. That means that it's not good to use models just picking just one grid point is not the thing to do. You have to look them at relatively larger areas and make an area average at most. So those models are also used to simulate future climate change, and this is summarized here. This is once again an IPCC diagram. So the way it is done is that it's done using different forcing conditions. So you have The part before 2000, this one takes the observation, so it's not the models. And then you have the different projections for different scenarios. In red, this is a scenario using CO2 forcing following what is called the RCP 8.5 pathway, which is more or less business as usual, so strong emissions of the different greenhouse gases. And below, another forcing scenario where you will take the a scenario which is the RCP 2.6, which is on aiming at mimicking a high policy or mitigation scenario, so trying to limit the temperature increase to 2 degrees. This 2 degree being temperature considered in the United Nations Convention on Climate Change as the limit to avoid the biggest threats to climate and humanity. And so the different models they are used with the forcing, and you can see that for each of the difference between the red and the blue are different forcings and different scenarios, and around the dark red or the dark blue are the multi-model mean. And around you see the range of the different simulations. So you have a range of answers by the different models. And on the right you have the maps associated with multi-model mean show you what the models tell about the different impacts of climate change, of impacts of increasing greenhouse gases. The higher scenarios, you have higher temperatures with some commonalities between the two maps, with more warming over land than oceans, and more warming and amplification in the north. And those are quite used and quite a strong basis for to study societal impacts. Those are projections, so they are with scenarios. They are not meant to be exactly what we could expect to happen. Indeed, predictions are. With predictions, we would like to be nearer to what may really happen in coming years. So what we call predictions will be more short-term, more than just 1 year. Often it's decadal predictions. We talk about decadal predictions, but they are initialized. So the idea is to initialize the ocean with some views that when initializing the ocean, you have some predictors of climate, some predictability due to the fact that you have information in the ocean. The atmosphere, we know that after 15 days, we are off. We are sure that we cannot predict exactly what is going to happen beyond 15 days due to turbulence. But with including some information in the ocean, we hope to have some more predictability of the system. There are uncertainties on that, so it's not prediction in. You cannot be sure indeed that it is exactly going to happen like this, but there are uncertainties on this. But it's more the idea to initialize and to be nearer to the past. What you see also in this diagram is that the first 20 years, there are no differences between the two scenarios. So the scenarios have mainly an impact beyond 20 years. So the first 20 years are more or less already determined, but by the emissions that have already happened in the past. This diagram is interesting to show you the different sources of uncertainties. It comes back to SEMIP 3, whatever. So in it's a paper in 2009, but it's important. The ideas are still there. The ideas are still the same, and I think it illustrates well this issue of uncertainties, and it's important for you to understand the different sources of uncertainties. They are quite different. They have a different nature, and it's important to understand them. So once again, it's the same. You have the different scenarios. Above top, you have, in this case, the 3 scenarios, and you have in color each model that has been drawn. So you see that you have variability of the different models around this mean, but you have also variability through time. If we look at the analyses, let's take the global one. There are different sources of this variability. You have what is called the internal variability. So the system is chaotic. So you have variability, and this is natural variability, internal variability of the system. You cannot omit that. So whatever you do, you will have an internal variability. This one, if you look at the start, it's relatively important, and you mainly see differences, not much by the scenario, but mainly by this internal variability. Then you have, when you look more through time, the scenario makes more difference between the different curves, and that's why the relative weight of scenario increases. It's not, it's just the relative weight of the different sources of uncertainty. And you have the models. You have between those different curves, the models are a source of uncertainty. If you take one scenario like the red one, you see that you have a range. This range is a combination of the different models and of the internal variability. Another way to look at it is the diagram on the right. This is a schematic diagram that was proposed from this Hawkins and Sutton paper. And it's another way to show the uncertainty. So the overall is the overall uncertainty, taking all the curves, and you have the relative weight, and you see that the natural variability, which is more the internal variability of part of the system, does not vary really through time. But then you have the uncertainty associated with the models in blue and the one associated with the scenario. So if you look on the longer term, the first uncertainty is the scenario, but this uncertainty is the one for which we can do something. That's the policy level where we can have some mitigation action and go towards one scenario or the other. The models, you cannot cope. You have uncertainty on the models, and I'm going next slide to discuss more this uncertainty related with the models. And the internal, you cannot cut it. You have an internal viability of the system. This is intrinsic to the system and to its chaotic nature. At the regional scale, this is the diagram in the middle, you have the relative weight, which is also given. And you see what is interesting, and that you see that when you look at more at the regional, the intermodal dependence is bigger. You have more variability between one model to the other at the regional scale. It is related to what I just showed you, that you have more dispersion between the models at the regional scale than at the larger scale. And you also have more internal variability. And so the scenario weight, the relative weight is smaller, but you have more, read it as having more weight of model uncertainty and more weight of internal variability when you look at a smaller scale. Next slide is on this model range. This is quite linked to what we call climate sensitivity. So if you take, for example, a doubling of CO2 and you look at the equilibrium response for under a doubling of CO2, the different models will give you an answer from 2 degrees to 4.5 degrees. And the mean of the models is about 3 degrees, but you will have a range from 2 to 4.5. And the analyses that are presented describe the different factors which are behind this answer by the models. If you look at the 3 degrees, so the mean, you will have the multimodal mean. The first answer, which is the dark blue, this is the Planck answer. So it's just the fact that when if you increase the forcing, so 4 watts per meter square for a doubling of CO2, you will have a 1.2 degree C answer. This is the direct radiative answer. Then you have the feedbacks above that. The light blue are the water vapor. If you increase temperature, you allow the atmosphere to have more water vapor. Water vapor is the first greenhouse gas. You will further increase to up to 2 degrees the answer. Then you have the albedo. If you increase temperature, you have less snow. You have a positive albedo feedback. And then you have in brown the cloud feedback. And so in average, you have a positive cloud feedback. But then if you look at those different factors on the right between the models, you see that between the models, the main difference between the models come from the clouds. So the cloud is the main uncertainty between the models. Some models tend to produce more high clouds, high level, high altitude clouds, we tend to have an important greenhouse effect, so they have an amplification effect. And some produce more lower clouds, which tend to have a more negative effect. And depending on where they put the clouds and how they produce the clouds, you have more or less cloud feedback. So this is the main reason for this range of uncertainty between the models. And it's quite difficult to really reduce this uncertainty. We know now better that the main problems come from low-level clouds in the shortwave that need to be improved. And there are still work ongoing, and we hope that SEMIP6 should improve. Still, there has been some work to try to better represent those low-level clouds. So what is SEMIP? SEMIP is Coupled Model Intercomparison Project. This is those projects under the World Climate Research Program. So they are not IPCC research. IPCC does not perform research. IPCC does an assessment of research. So SEMIP is organized through the World Climate Research Program. And it has been done to foster the development and review of coupled models. It started in 1995. The various stages have been quite linked with IPCC. So IPCC gives the phasing, the timing of those exercises, because the idea is to have those exercises ready to be used in IPCC assessment reports. And mainly the results I'm showing are from SEMIP5 that was prepared for R5, and SEMIP6 is the new, the latest one, which still many papers have been, most of the papers have been sent in 2019. They are still under publication, and AR6 is going to be in 2021. Maybe, sorry, there is a mistake. The publication is in 2021. And will be quite important to have a good synthesis of all what has been produced. At each time, you see that the amount of data is increasing for several reasons. Mainly, the resolution of model is increasing, producing more data, more models worldwide, and more countries interested to participate to this exercise, and more data available for impact studies, required for impact studies. Those SEMIP, what is important is to understand is that what you see most of the time are the projections and predictions for the short term. But it's not the only objective. It's just one part. The exercise is really built to give you projections, but also a strong basis for evaluation. And I showed one example, but also mechanism. There are sensitivity experiments to better understand, for example, here, understand the role of low-level clouds compared to some satellite observations. Just an overview, SEMIP5, SEMIP6, that's a large number of experiments. You have to realize that it's most of the time it's several thousand or even 10,000 simulated years associated with all the simulations, the projections being only one part. and you have the different set of MIPs. MIPs are model intercomparison project. Myself, I was strongly involved in the past in PMIP, so launching the paleoclimates since 1891. And you have a range of other MIPs, some focusing on land use, better understanding land use, chemistry, doing better understanding the ocean, the clouds, and even in SEMIP 6, some geoengineering. To give you, I'm not going in all the details for SEMIP 5, for example, you have where the simulations are run. Typically, 1 in Canada, 6 in the US, 7 in Europe, 1 in Russia, 5 in China, 1 in Korea, 4 in Japan, 2 in Australia. And at each time, you can see that for each modeling group, institution, you have a range of model configurations. So often you have several configurations at different resolutions or for different complexity of the models. So for example, for SEMIP 5, about 28 modeling groups, 61 model configurations. And to show you in Europe, the way it is organized, you have a consortium, which is called EC-Earth, that is using the European SMWF model in a climate version, and that gathers different countries. It's led by Sweden. There is a strong involvement in Netherlands, in Spain, in Italy, so different countries. You also have models that are developed in one country. Like, for example, in France, we have 2 climate models. One which is academic community, the other one based on the weather forecast model. In Germany, you have the Max Planck model. In Italy, the CMCC is a consortium also in Italy having their own models. In UK, you have the Hadley family, or the UK, more and more integrated in UK and in Norway. So you see a range of models. This slide just shows that mainly those models use different components, but you have in color when they share some components. For example, they share the coupler. Several of them share NEMO, which is a common ocean platform. Then the other components, they differ from one model to the other. An analysis that has been done by Knutti on SEMIP 5 is interesting. That shows you that you have the range of different models on the left. You have some are for SEMIP 3, some are with a star for SEMIP 5, whatever. And I have emphasized the European ones. And on the right, it shows the neighboring. So looking at surface air temperature and precipitations is how far they have similar patterns, how far they are in their representation of surface air temperature and precipitation. And it's interesting to see, for example, the smallest horizontal bars shows that they are near, and when it is bigger, they are further apart. And there are some similarities. For example, if I take the French Météo France, CNRM, and EC-Earth, there are some similarities, but it happens that their atmospheric circulation is based both on IFS, and the similarities often seem to be quite linked with the atmosphere. So the models that use the same atmosphere tend to have more similar answers in surface air temperature and precipitation. It's not the whole of the story, but it shows that there are some similarities. So the models, they are not fully independent from one to another, but so it shows that there are some similarities. So it's a bit complex, and to know which one to use, we have to take care not to use only the models that are the nearest in the similarity. It's good to use a range of models quite different from one another. The model data, there is a strong effort, and in ES-ENES we are strongly involved in this part to have a common data infrastructure where people can access the data in data nodes. They have index nodes to search the different data, with the idea that the data are stored at different locations, but for the people, they are seen at just one database. You don't know where they are. It's not the issue, but you can access the overall. We reach orders of magnitude which are very big. We are in the petabyte scale, particularly with SEMIP 6. There are about 9 petabytes back without replica, and with replica we reach 16 petabyte of data. We are so quite on a high range of heavy database, and with 15,000 registered users, so quite used worldwide. So in ES-ENES, we support this infrastructure. We support ESGF, which is the Earth System Grid Federation. And also we support a portal like the Climate for Impact portal, which should help you accessing those data. So you will know more when you will go along the other courses, but just to let you know where we are in ES-ENES, and for us it's important to be sure that those data are well and easily accessible. We also make the interface with Copernicus, so we make sure that the climate projections are available in the Copernicus climate change service. So we are quite involved in that as well. We have a scale issue, as I mentioned. When you go with a GCM that is at 100 kilometer scale, you are missing elements like the topography. So SEMIP 5 has been quite used to within CORDEX, the Coordinated Regional Downscaling Experiment, also coordinated by WCRP, the World Climate Research Programme, to derive some regional downscaled information. So with higher spatial resolution, like 12 kilometer or 40 kilometer, either dynamically or through statistical approach, and you will have other lectures that will go more on this. But to show you on the right, an example on the precipitation over the Alps that clearly shows that below, at the bottom, you have the Euro 4 AIM analysis at regional scale, and that shows you that the way that precipitation is in the Alps is quite dependent on the orography on the spatial scale. So often, most often, the impact studies are done using CORDEX, but not necessarily only. For example, the SEMIP, which is an intersectoral impact MIP, has used directly the SEMIP 5 data, debiased, because there are biases in the model. So there is a need to avoid to have the main bias. For example, the easiest way to debias is to take an anomaly of temperature and add this to the climatology. But there are other more accurate ways of debiasing, for example, keeping the statistics a better shape of the statistics, not only on the mean. And here are two examples of ways to use those data for impacts. For example, on top right, results by Varsovsky et al. Showing the temperature at which ecosystem become at risk, where you show that there are some places where very high latitudes where it can become at risk even for a small increase of temperature like 1 or 1.5 degree. And for other boreal regions, you are at risk with a 3 to 4 degree C of increase. So that's one impact study. Another one, top left, on malaria. If you take the scenario RCP H2020 IS-ENES, in blue, that's where you will have a decrease of malaria. In red, an increase. It shows you that with a high, strong temperature increase, you can have less malaria because the mosquitoes do not like when the temperature is too warm. But then you will have some regions that up to now do not experience malaria, like Eastern Africa, where you may now, in the future, with a high scenario, may experience malaria conditions. So shows you two examples that those data are then can be used to do impact studies at global scale or at more regional scale. The way we proceed is the diagram below shows you that typically we have an ensemble of global models. So ensemble in this case meaning different models, but also sometimes different initial states of those models. That's the two ways to have an ensemble. And from those ensemble, we derive an ensemble of regional models, that's Cordex. For SEMIP6, we are at highest complexity, we are at 30 kilometers. There will be coming, I guess in coming years, ensembles at 2, 3, 5 kilometers for, or 10 kilometers for Cordex. And gradually we increase that. The problem is that we increase, but relatively slowly due to the, we have to follow the progress of the computers. And we see as a grand challenge that ideally it would be good if we could reach the kilometer scale for those global models, because then we would be able to resolve deep convection and small scale ADs in the ocean. And that would be really a great expected great progress. But so there is but this is very demanding in computing, very demanding in improving, accelerating the progress in computing efficiency. And we are not there yet, but that's something that for which the community thinks that it would be quite pushing and be quite an added value, but it will take some time. It's just to show you a few results of SEMIP6. They are just coming out. For example, this paper is just issued in April 2020. So we are just showing you, it's interesting, top left compared to observations in dark, in black. You have SEMIP3 in green, SEMIP5 in red, SEMIP6 in blue, showing that SEMIP6 tend to reproduce quite well the historical temperature increase. On the right, the same diagram as the one I showed you, but this time for including SEMIP6, that shows you that the model are improving in SEMIP6 compared to SEMIP5, but still with some uncertainty range. And bottom left is an interesting one. It's the climate sensitivity. Indeed, SEMIP6 models tend to have a higher climate sensitivity than SEMIP5, which are in orange, or SEMIP3 in blue. This is something which will need to be assessed within AR6, and will be interesting to see whether this is so. A lot of work has been done to improve the representation of clouds, but consequently, they tend to have a relatively higher sensitivity, and not just one model, several models, several of those models have these. So we'll have in AR6, it will be important to have the assessment of this change. So to conclude, I hope that it allows to show you that they are key, those models are key tools to understand mechanism and say something about possible future change. The SEMIP cycles play a key role. They are reference set of simulations. At each cycle, there are improvements. It's clear that SEMIP5 is very well documented. SEMIP6 is now available, but still under documentation phase. Europe is a key player in this international landscape with several of those models, but also with a support to the infrastructure with ENES. We see that in the future, there is a grand challenge towards very high resolution, but not only, there is also a need to have larger ensembles, better account for complexity. So climate models are the core of the climate information for society, and it's important, we think it's important that you, and we hope this autumn school will help you really better use the data from those reference simulations, and that you will enjoy this school. Thank you.